Okay, good morning. Can you hear me? Can you see the blackboard?
Yes, sir.
Today we have two chapters, but just 3 pages for each one, and which is a short lecture. We will talk about gravity, compressor, and tides, and also we'll talk about waves and sound and Doppler. The same will be for the last lecture. Will be 2 chapters, but they are short, as I told you from before. Okay, now starting talking about gravity. If you remember, we are the founder of the gravity is not Newton. Gravity is a natural law. It's a natural law, but the physics by Newton is created, or Newton he put the law of gravity, which is a physical law. As we know by Newton, we have the first, second, and the third law. Also, we have the law of gravity. All of them in nature, they have their nature properties, and they are nature laws. But our scientists here put the mathematical law for them. Now, if we have, now we'll talk about the gravity. If we have 2 objects, mass 1 and another mass, m2, there is a distance between them. And this distance from m1 to m2, it is r1, 2, from 1 to 2. Also, it is the same distance from 2 to 1. So we have r12 and r1 to r21. There is a force between these 2 objects, and this force is due gravity. And like any law in physics, for example, if we take this F is equal to ma. If we increase m, then F will increase. If we increase a, then F will increase also, and so on. This is a dependence. Also here we have a dependence for this force, which is attractive force. We have F from 2 on 1. Also we have another force from 1 on 2. And as you know, they are equal to each other with negative sign for the direction. Okay, this force F from 2 on 1, for example, it depends on the mass of 2 over the radius from 2 to 1. As we say, it is the same as the force from 1 to 2. It is the same. Also, it depends on the first mass over its radius from 1 to 2. It depends on the first mass. And opposite dependence on the radius or the distance from 1 to 2. Also, it depends oppositely with the radius from R2 to 1, as we see it from here. But R21 is equal to R12. F12 is equal to F21. So we will remove these sub-indices because they are the same. In physics, if we have any dependence relation, to convert it to equal relation, we need to put a constant. And this constant here is found experimentally and theoretically. It is G, which is the universal constant for gravity. And the force will be M1, M2 over R squared multiplied by V. This is the force of the attractive gravity. It is measured by Newton. It is a force. So it's just an attractive force. There is no repulsion force. If you remember, and you know that, if we have negative charge with positive charge, the force is attractive. If we have another negative charge here, the force is repulsion, right? Or repulsive. Also the same for the magnetic force. But for gravity, always it is attractive. This G constant, it is different than G, which is the acceleration, which is 9.8 at Earth surface. This G, it is equal to 6.67, I think, multiplied by 10 to minus 11 newtons meter square over kilogram square. It's a constant. It's the same all over the universe. At the Earth's surface, at the sun, in deep universe distances like that, it is constant. Okay, what else? Any question about this concept? I just will solve examples. And from these examples, you will see the dependence of this force on the mass and the radius. If the mass is small, then the force is small. If the radius is big, then the force is small. The first page, we have this example. We have the Earth surface. And this is a person with mass M1, M1. This is important thing also. Please take care of this. This is the air. This is the radius of the air. The distance here, R, it is the distance between the centers, which is the center of gravity or the center of mass. As we know from before, we need to deal with the center of mass or free body diagram. So we need to consider all of this body just as a point. Okay. And we have the mass of Earth, which is ME. This is M1. And this person, like me, his center of mass is approximately 1 meter above the ground, which is almost here. Okay? So I will assume this distance as R1, I think, or R for this mass, which is equal to 1 meter. The radius for the air is equal to 6,000 kilometers. 6,000 kilometers, yes, which is 6.37 multiplied by 10 to 6 meters. 6,000 kilometers. And the mass of air is very big, which is 6 multiplied by 10 to 24 kilograms. And my mass, for example, it is, no, not one, not me. 70 kilograms. And R1 is equal to 1 meter. Okay? Now we need to find the gravitational force between these two objects. In physics, yes, these are just two objects. We don't care about them if they are planets, person and planet, just object. Okay? Now to find the distance, we need the distance between the two centers. This is the center of air. And this is the center of this person in his stomach here. This is the distance between them. We need to consider this distance in our calculations. This is the force of gravity is equal to G, which is a constant. M1 multiplied by M2 over R squared. What is R? R, it is the total distance from the center of air to the center of this person. R is equal to the radius of air plus the radius of this man. Okay, the radius of air is 6 million meters, which is 6, 3, 7, 1, 1, 2, 3, plus 1. So we can put the 1 added here. But it is not logical to keep this 1 in our calculations here. It will not affect. Before 2 days, I weighed myself and I found myself 91 kilograms. I like to lose some weight just by doing something. What I did, I go and cut my hair. Okay, and after cutting my hair, I measure my weight. What do you think? Is it 81, for example, or 89? No, it is just 91. It is not affected to my weight. Also, this one, it will not affect to this distance. So, from this, we need just to take, because they are at the surface of the air, R is just R, the radius of the air. Okay, but if we are dealing with Earth and the moon, no, we need to consider everything. Okay, but the mass of this mass M1 and this is mass of air, they are multiplied together. It's okay to keep them. Okay, we cannot consider this mass as 0. If we multiply 0 by this, it will be 0, but we cannot do that. So, in this case, we need to consider our distance is the distance of the radius of air. Okay? Okay. Now, let us continue. Okay, it is equal to 6.67 E minus 11. You know this E, it means 10 to minus 11. You can see it in your calculator. Okay, and the programming you use it. The first mass, it is 70. The mass of Earth is 6 multiplied 10 to 24, yes. It's 24 kilograms. It's very 24 zeros. Over the radius, which is 6.36 multiplied by 10 to 6 squared. You can use your calculator directly to solve that. This will give you 690.7 newtons. This is the force of gravity, or capital G. I'll put it capital G. Okay, keep this in your mind. And remember the weight. What is the weight? The weight is the force of gravity. The weight is equal to mg, which is equal to m, which is 70, multiplied by 9.8. By the way, 9.8 is approximated value. I will tell you the right one now. I had 9.8. This will be equal to 70 multiplied 9.8. It is equal to 686 6 newtons. 690.7, 686. It is just 4 newtons. It's very like this, maybe. It's just 4 newtons. So the force of gravity is the same as the weight. I approximated G here, but in this calculator, I have G stored. I know that. The actual value of G was G. It's what it is. I'll do it. Okay, fun. Okay. This is the way. Line point, the same thing. Okay, keep the way. طيب. Let me now calculate the acceleration and I will show you the actual value of G. What if I need to calculate the acceleration if this object needs to accelerate downward? We have two accelerations. The acceleration will be computed by using Newton's second law, which is F is equal to ma. I need to calculate the acceleration for the man, which is m1. It is equal to its mass. The force is the same. Now look, the force is the same between the two objects. The force from Earth on the map is 690 newtons downward. And the force from the man on the Earth is the same thing. Okay? So the man will attract the Earth to its center. Now the force is equal to 690.7, which is equal to the mass. I need to calculate the acceleration of the mass, the man, which is 70, multiplied by its acceleration. Then the acceleration divided over 70. The acceleration of the man is equal to 690.7 over 70. This will be equal to 9.867, and we have something 14 meter per square second. This is the actual value of G. We computed it now. It is not just 9.8. We have something else also. Okay. Because of that, we approximated to 9.8 or to 10. So this is the acceleration due to gravity, which is G. Now, what is the acceleration? And this is the value what I'm looking here on this is not my calculator. So it's a new one. Now, what's the acceleration of the sun? Okay, for the sun, no, the earth, I'm sorry. The force on the earth, it is the same magnitude, but the opposite direction. So the force is the same, 690.7 is equal to the mass of air multiplied by its acceleration. If I need to compute the acceleration of the air, it will be equal to the force divided over its mass, which is 6 multiplied by 10 to 24. In this case, it will be something very, very small. It is 1.15 multiplied by 10 to negative 22 meters per second. So every 1.15, 10 to negative 22, the earth will move. This is in second. In each second, the earth will accelerate by this amount, which is almost zero. Okay, so there is acceleration from me on earth. So if I ask you, if all the people we put them here at this point, we have 7.5 billions, which is multiplied by 10 to the 9 people. Then if we multiply this number by this number, it will still very small. It will be negative 13, for example. So the earth will not affect by all the people of the earth, also by all the masses, which are the buildings. If we put them in just one side, it will not affect, because the earth is very big, its mass. Is this point clear? Now I will solve another example with different masses, with different objects. If we have, for example, two persons, the distance between them is 5 meters. This is M1, 60 kilograms. This is 70 kilograms, which is M2. Look, when we solve this force, we have G is negative 211, small. We have the mass of Earth is big. We have the radius of Earth is big, almost. Now we have small masses and small distance, which is just 5 meters. Okay, what is the force between these two persons? It is equal to G is 6.67 multiplied 10 minus 11. Okay. Multiplied by the masses, which is 60, 70 over the mass square, which is 25. This will be equal to, I'll solve it now. Okay, clear. I'll do this 6.67. Multiplied by 60, 70 over 5 square. Where is square? Okay. Okay. It is 1.12 multiplied by 10 to negative 8 newtons. It is very, very small force. But in you can compute also the acceleration. The acceleration is equal to the force over any mass. The acceleration of the first mass is the force over the first mass. This can be done in the lab. Okay, what about the next example? We have different masses, different distance between them. In outer space, we have satellite and space shuttle. And we have okay. The distance between them is 1,000 meters, which is a kilometer. This is M2 equal to 80,000 kilograms. This may be M1 is equal to 3. Maybe it's the station. Okay, what is the force between them? The same thing. F between 1 and 2, which is equal to F between 2 and 1, which is equal to 6.67 multiplied by 10 to negative 11 multiplied by the masses, which is 30,000 multiplied by 80,000 over the distance squared, which is a million. Now again, repeat everything. Like 30,000 multiplied by 80,000 divided over 1,000 squared. Okay. Did you do that? Is it 1.6 multiplied by 10 to the negative 7 newtons? Right? Thank you. Okay, it is a small also. We have big masses. We have distance 1,000, but it is small. What about 2 stars, 2 galaxies? We can do that also. It's the same thing. For the large distance and the small masses, compared to these distances, we just need to use Newton's law in gravity. We don't need to use the general relativity laws to do that. If we have the Earth and we have the Sun and the Alpha Centauri here, it's far away from them. Maybe 4 light years, which is 4.37 light year. It's a distance. Each one light year is equal to, I think you do that in the lab, it is equal to 9.5 multiplied by 10 to 15 meters. It is a distance. So I need to convert this to meters, to distance. So before starting solving anything. Okay. Now the distance. It's 4.37 light year. I need to multiply it by the 1, which is the coefficient of conversion. as I told you, the first lecture is not required in the final exam, but our material depends on it. Okay? So be careful about this. Don't just tell yourself the final exam is not comprehensive. It contains everything. Okay. Now I need to multiply by the coefficient of convergence, which is 1. No, not 1. 1 light year is equal to 9.5 multiplied to 10 by 10 to 15 meters. Now light year will cancel with the light year. So this is my distance. How much is it? Tell me, please. You compute it? It's okay. 4.37 multiplied by 9.5. It is 41.515 multiplied by 10 to 15 meters. This is very far. Not very. Okay. Sorry. This is the distance. Now I need to put it here to square it. I need to use the mass of Earth, the mass of the sun, the mass of Alpha Centauri. This is Alpha Centauri. Okay? It is the closest star to us. The light required 4.37 years to arrive. When we look at it, we see it before 4 years. Okay. Now, where's the mass of the Earth? As we see, it is 6 point, no, without point, multiplied to 24 kilograms. The mass of the sun is equal to, let's figure, 2 multiplied by 10 to 30 kilograms. It's 1,000,000 times bigger than the Earth's mass. The mass of Alpha Centauri is equal to, smaller than the sun, yes, 2.45 multiplied by 10 to 29 kilograms. If you need now to find the distance from the solar system, which is the sun and the Earth, with Alpha is the same. Okay, the distance from the Earth to Alpha Centauri, or from the sun to Alpha Centauri. The distance from Earth to the sun, I think it is 1.5 multiplied by 10 to 9 meters. You can find the force between any of these three objects in a Newton. So if I ask you to find the force between Earth and sun, it is equal G. I will put it there, we know the formula. It is 6.67 e to minus 11 . I need to compare now with you the force from the sun on the Earth and the force from the far star on Earth. If it is a black hole, for example, or a galaxy, the mass will be much, much higher than this. Okay, not too much higher. Okay, for the black hole. The mass of the Earth, which is 6e24. The mass of the sun is 2e30. The distance is 1.5 e9 squared. Yes, I'm right. Okay. Again, it is 6.67. 10 to the 11. Multiplied by the mass, which is 6 multiplied by 10 to 24. Multiplied by 2, 10 to 30. Second goes divided over 1.5 multiplied by 10 to the 9. Now, second goes to be a second goes. Okay. It is not small, okay? 3.5573 multiplied by 10 to 26 newtons. It should be big because the earth is huge and the sun is huge. And if the force is just 10 newtons, then the earth will escape from the sun with any by doing any force on it. This is the force between the earth and the sun. I'm sorry about this. The air. This is the sun. Now this is the force. It is very strong. It's of the rank 10 to 26 newtons. What about the force between Earth and Alpha Centauri, which is so far away? Okay, the force between Earth and Alpha Centauri, it is equal to 6.67 E-11. The mass of the Earth is again 6E24. The mass of that one is 2.45 E to 29. It's the same almost as the sun. Over the distance, which is how much it was? 41.515. Okay. 41.515 E 15 squared. Wow. Okay. Let me do it again. It is 2.45 multiplied by 10 to 29. Okay, second goes. For 1.515 multiplied by 1015. Second goes. Square second goes. It's not small. It is not small also. It is something multiplied by 10 to the 10. It's between Earth and Alpha Centauri. So the force between the Earth and Alpha Centauri from this rank in newtons, but this 26 is too much bigger than this. Because of that, the gravity of the sun dominates everything. Okay, But we have a gravity bit between Alpha Centauri and the Earth, which is a far away star. If this star is disappeared immediately, then we have this effect on our system. But this will be dominated by this one. Do not imagine that will affect too much on us. It is just when as a fly come to our hand and go away from our hand. It will affect us. The answer is not. It's no. Okay. Okay, now we have any questions about Newton's law? Now we have Kepler's laws and tides. These topics, graphics, yes, and videos are better to describe the things. Kepler's laws, this is the sun, this is the planets, these are planets around the sun. Kepler's laws are the laws that control or describe the motion of these objects around the sun. Not just this system, also the galaxies or any objects rotating around the center of mass. The tides, you know about the tides, which happened on the seas on Earth. Now I will play these videos. We need to watch them. Share my monitor. Okay. Can you see my monitor live?
Yes.
Okay, thank you. Now, before we move to waves and sound, we need to start with Kepler's law. It's a YouTube video.
Clean the stable of the strong circles and spirals.
This is Carl Sagan.
With only a single cartful of dung. He tried various oval-like curves, calculated away, made some arithmetical mistakes, which caused him, in fact, to reject the correct answer. And months later, in some desperation, tried the formula for the first time for an ellipse. The ellipse matched the observations of Tycho beautifully. In such an orbit, the sun is not at the center, but is offset. It's at one focus of the ellipse. When a given planet is at the far point in its orbit from the sun, it goes more slowly. As it approaches the near point, it speeds up. Such motion is why we describe the planets as forever falling towards the sun, but never reaching it. Kepler's first law of planetary motion is simply this. A planet moves in an ellipse with the sun at one focus. As the planet moves along its orbit, it sweeps out in a given period of time an imaginary wedge-shaped area. When the planet is far from the sun, the area is long and thin. When the planet is close to the sun, the area is short and squat. Although the shapes of these wedges are different, Kepler found that their areas are exactly the same. This provided a precise mathematical description of how a planet changes its speed in relation to its distance from the sun. Now, for the first time, astronomers could predict exactly where a planet would be in accordance with a simple and invariable law. Kepler's second law is this. A planet sweeps out equal areas in equal times. Kepler's first two laws of planetary motion may seem a little remote and abstract. All right, planets move in ellipses and they sweep out equal areas in equal times. So what? It's not as easy to grasp as circular motion. We might have a tendency to dismiss it, to say it's a mere mathematical tinkering, something removed from everyday life. But these are the laws our planet itself obeys, as we, glued by gravity to the surface of the Earth, hurtle through space. We move in accord with laws of nature, which Kepler first discovered. When we send spacecraft to the planets, when we observe double stars, when we examine the motion of distant galaxies, we find that all over the universe, Kepler's laws are obeyed. Many years later, Kepler came upon his third and last law of planetary motion, a law which relates the motion of the various planets to each other, which lays out correctly the clockwork of the solar system. He discovered a simple mathematical relationship between the size of a planet's orbit and the average speed at which it travels around the sun. This confirmed his long-held belief that there must be a force in the sun that drives the planets, a force stronger for the inner fast-moving planets and weaker for the outer slow-moving planets. Isaac Newton later identified that force as gravity, answering at last the fundamental question, what makes the planets go? Kepler's third or harmonic law states that the squares of the periods of the planets, the time for them to make one orbit, are proportional to the cubes, the third power, of their average distances from the sun. So the further away a planet is from the sun, the slower it moves, but according to a precise mathematical law.
New Ocean Spray Fruit Medley. Boom.
Okay. Is it understood, this video? You can see it many times on YouTube. Now we'll talk about the tides. This is the first video about the tide.
This shows 12 hours at the famous Bay of Fundy in Nova Scotia, Canada. It's the biggest tide change in the world. But what force could move such a massive body of water? Gravity. Here's the Earth rotating on its axis every 24 hours. We'll now draw the Earth as a diagram with its surrounding layer of ocean. And to the right is the silvery moon. Everything is attracted to everything else in the universe with the force of gravity. So the moon is attracted to the Earth, and the Earth is equally attracted to the moon. Notice that the two force arrows are the same length, showing that gravitational attractions are of equal strength. But we're only interested in the force on the Earth here. The moon pulls on the ocean closest to it and makes it bulge outwards. When the Earth rotates, the sea level is higher at this point in its rotation, causing a high tide. And a low tide where the oceans don't bulge. So you'd expect one high tide each day. But here it gets interesting because there are two high tides a day. How come? This is because the strength of gravity is greater when objects are closer. We'll call the location of the ocean on the near side of the moon point A, at the centre of the Earth point B, and at the far side ocean point C. The strength of the moon's gravity is strongest at A because it's closest to the moon. So the part of the ocean that bulges towards the moon most is at A. But the moon's gravity also pulls on the Earth, moving it towards the moon as well. This has two effects. First, it makes another bulge at C. Second, it fills in the bulge at A, but not completely, because A has moved further towards the moon than B. Lastly, the far side ocean at C is also attracted to the moon. but it moves least because the moon's gravitational pull here is at its weakest, being farthest from the moon. This leaves a partial bulge at C, though not as big as the one at A. Now we can see why, when the Earth rotates through 24 hours, it goes through 2 high tides and 2 low tides. But there's another surprise. By the time the Earth has rotated once and arrived back at its original position, the moon has moved on a bit because it's orbiting the Earth at the same time. That means that the Earth has to catch up with the moon, so the next day's high tide is about 50 minutes later. The moon rises and sets about 50 minutes later too, because the Earth has to catch up with its orbiting moon. You can even test this by timing the moon rise or moon set from one day to the next. Or check out some tide charts to see if the tides obey this rule too.
Okay, now we will see now the sun effect plus the moon effect time.
It's time to help people customize and save with Liberty Mutual.
Tides are caused by the moon's gravitational force pulling on the Earth and its oceans with different strengths. The pull on the near-side ocean is the strongest because it's the closest, so it moves most towards the moon. The Earth also moves towards the moon, but not so much as it's further away. Finally, the far-side ocean moves towards the moon least because it's farthest from the moon. These movements due to gravity create 2 high tides and 2 low tides as the Earth rotates through 24 hours. But there's a big object that's missing from our diagram. If we back up, we can also see the sun and how it lights up both the Earth and the moon into their day and night sides. We'll turn off the stars to make it clearer. When the moon is right in front of the sun, it's invisible to us because we can only see its dark night side. This is the new moon position. You can see that each day corresponds to 1 Earth rotation. In just over 7 days, that is 7 Earth rotations. The moon orbits around the Earth to its first quarter position, where we can see half its day and half its night side.
Look at the tide direction.
After another 7 days or so, the moon orbits to the opposite side of the Earth, to the sun, and we can see its full day side. This is the full moon. Then it continues on to the 3rd quarter before returning to the new moon position to start all over again. Does the sun also pull on the oceans and make them bulge like the moon does? Yes, everything causes gravity, And the more massive the object, the stronger it is. But this diagram isn't to scale, and the sun's much further away than the moon, reducing its tidal effect to about half that of the moon's. But this is important when the sun and moon line up so their gravitational attractions combine to make super tides. This happens at the new moon, making the high tides higher and the low tides lower. This extreme tide is called a spring tide. But when the moon goes into the first quarter, the gravities pull in different directions, and the sun actually takes away from the moon's tidal effect. The high tides are not so high and the low tides are not so low. This more moderate tide is called a neap tide. At the full moon, the moon and sun's gravities line up again, so we get another spring tide. At the third quarter, the gravities are out of whack again, so we get another neap tide. Then back at the new moon position, the moon's gravity combines with the sun's to start over again with another spring tide. Each month, the Earth spins almost 30 times, so we get nearly 60 high tides and 60 low tides. Of these, 2 are spring tides and 2 are neap tides.
Okay, we'll now stop sharing. I think my language will not be good enough to say like these videos. Now it is required in the exam. Maybe I will ask you how many tides, how the tides and patterns happen. Okay. I will ask you about the Kepler's laws. It is simple to be understood. Okay. And as you see, I put matching questions. Second, I will use that. First, this also in the final exam. Now we have another topic, which is the waves and the sound. Waves. You will see, you know about this topic. The wave. We have, this is a wave. We see this from before. We have another type of wave. For this wave, this is the source. Here. Okay. We have another type. We have 2 types of the waves, depending on the shape of the wave. And now, for this wave, it is a transverse wave. The particle of the matter vibrating, for example, water surface is vibrating. If you put any piece of wood or plastic, you throw a stone, you will see the waves going away from the center. But your piece of plastic or wood will move just up and down. It will not move away. from the center of the source, okay? So the particles will move up and down, and the propagation direction is forward. So this wave is a transverse wave, which has the vibration is perpendicular to the direction of motion or the direction of the wave. This is just like the waves happened in a rope, okay? Also, the electromagnetic waves, the light is waves. The electromagnetic waves, which is the like microwaves, the X-ray, the ultraviolet, and so on. It's kinds of waves, and these waves is vibrating, and you can see many videos about that. Right? These waves may move in a matter like water, surface vibrations, or in vacuum, like the electromagnetic waves. For example, the light doesn't need any matter or material or medium to transfer from sun to us. For these waves, the particles of the vibrating material is vibrating forward and backward like this, and the motion, propagation to this direction. This is longitudinal waves, and which is defined as the vibration of the medium is in the same direction of the propagation direction that way. It is just, it needs this needs matter. It doesn't move in the vacuum. This is matter, okay? And we have the vacuum. It doesn't move in vacuum. Like the sound. The sound is moving in air. The velocity of sound for the sound in vacuum is 0. So for astronauts, 2 astronauts, the velocity of the sound between them is 0. They cannot hear themselves, and the sound needs infinity time to reach from one to another. Also, you can hear here using solid materials to hear sound or waves. Also, the earthquake waves, it is which is the seismic waves. It's a sound wave, kind of a sound wave. The velocity in this is about sound, okay? Okay. Now, as you know from before, for each wave, there is a wavelength, lambda. Also, there is a time period, which is equal to 1 over the frequency. Lambda is a length, okay? We can consider, look at this point here. We can consider lambda as a length as x, a distance from point to point. The time period from, if we are here in this wave and this wave moves to here, it needs a time, capital T. What's its velocity? The velocity is the displacement, which is x, over the time. But x is lambda. So the velocity of the wave is lambda over the time. Okay, the time is equal 1 over the frequency. I can put it like this, lambda over 1 over frequency. So the velocity is equal to, I can put this, lambda multiplied by the frequency. Or lambda is equal to the velocity over the frequency, or the frequency is equal to the velocity divided over the wavelength. So the speed of sound can be computed by that. The speed of light, which is electromagnetic wave, it's a wave. Everything is a wave. Can be computed by this. Okay. Any question about waves? Huh? Now, for example, we can hear the sound through the air. Its speed, velocity. The velocity of the sound in air is equal to 343 meters per second. So if any person is away from you, not half a mile, maybe 400 or less yards, or 343 meters, you will hear his voice after a second. Because of that, you can see the light from the clouds before the sound or the storms, right? Also, and if you look to your friend and he is far away from you, maybe more than 300 or 400 meters, and he shaking to you and screaming to you, you will see his hand, but you will hear his voice after maybe 1 second, 2 seconds, that's all. Also, another thing, previously, the shape keepers, there's the train lanes. As you know, it's an arrow, okay? When the train came, the shapes go and came and they are very afraid, and some of them come under the wheels of that train. Because of that, these keepers, they need to know when the train will come to go away, take their sheep away from this place, from that lanes. They're just doing this. They will hear the sound of the train, maybe 10 kilometers away from them, because the sound is faster in solids. Also, the sound is faster in solids, the fastest, okay? In water, for example, it is faster than the air, but not faster than the solids. Because of that, the sound is fast in water. Many water creatures like whales and any other creatures contact with each other using the sound. We will talk about the kinds of the sound or the waves frequencies. Now let us, in page number 1 in this topic, solve this example. We have two signals, wave signals. One of them is sound, the other is light. Any question about waves? We have transverse, just like light, or the waves on the surface of water, and we have longitudinal waves, just like the sound. Now, we have this example. We have two signals. The first one, it is a sound wave with velocity in air 343 meters per second, and frequency, which is 1/t, it is equal to 45,000 hertz. You know that the frequency unit is in hertz. What is the velocity? No, not the velocity. We have this law, simply. Lambda is equal to OV over the frequency. What is lambda? I need just to find lambda, the wavelength. Yes, I didn't told you for this wave. This is a compression. This is a compression, this is decompression. This is a compression. This is the same as this. Okay. This is a wavelength from here to here. For us, we need a full wavelength. It will be like this. I'll remove it again. But it will be like this. This is maybe our wavelength for transverse wave, okay? For the longitudinal waves, the wavelength is the distance between two compressions. Okay, we have a wavelength here. We have a time period, that's all. Now, lambda, which is the wavelength in sound case, it is the velocity divided over the frequency. I have the formula, it is 343 over 45,000 hertz. It will be 7.62 meters. So the wavelength is 7 meters. It is almost the width of this hole. This is a wave. 7 meters, or the board, maybe it's 7 meters. Okay, what else? What is the period? The time period is 1 over the frequency, which is 1 over this, which is equal to 2.2 multiplied by 10 to negative 5 seconds. So the wave needs to move this distance 7 meters. 2 multiplied by 10 to minus 5 seconds. It's very fast. Not very fast, 343 meters per second. What about the light? Now the light, for example, we have colors. Each color has its length, wavelength, and its frequency. For example, in our example, we have the green light. Okay, we have the frequency is equal to 5.45 multiplied by 10 to 14 hertz. And the velocity is the speed of light, which is sometimes we write it 3 multiplied by 10 to 8 meters per second, but actually it is 29979, how much better? 2458 meter per second. It is 2.9979 multiplied by 10 to 8. It's the same. Okay. What we need to find? We need to find lambda, the wavelength for the green light. You will see it is the velocity over the frequency. This over this, it will be equal to 5.49 multiplied by 10 to negative 7 meters. It is very short, which is equal to 0.55 almost. I round this micrometer. Micro, which is 10 to minus 6. Okay. And the time period, it is 1 over the frequency, which is 5.45 multiplied by 10 to 14. So the time period to pass this length, it is 1.8 something multiplied by 10 to negative 15, I think. Yes, 15 second. It's a femtosecond. Femtosecond. Now look to compare between the wave, the sound wave, and the light wave. The sound wave length is 7 meters. It is just like this board twice. Okay? This is the sound. But the light signal, it is almost half a micrometer, which is half over a million. This is the wavelength for the light. It's very short. Okay, there is a difference between them. Any question about this? Now, the second page, as I said before, the wave is the sound is longitudinal waves, and if you look at this table from the book, you will see the speed of sound in each material, in aluminum to air. In vacuum, the speed is 0. Okay. In air, it's 343 at 20 degrees. But in aluminum, it's 6,420 meters per second. So steel, 5,960 meters per second. So you can hear the train when he far away from you, when it's far away from you, 7 kilometers before just 1 second. Okay. Now for the sound waves, we have 3 bands or 3 types of these sound waves, as you see. We have the sonic or the hair to us. The sound, as you see, we will talk about the frequency. A human can hear frequency from 20 hertz to 20,000, I think, hertz. Let me be sure about that. I think yes. Okay. Now, here we can hear that. Plus minus something. Depends on person and depends on the his ear property. Okay. Any frequency above this frequency it is ultra sonic. Here, any frequency below 20 hertz, it's infra sonic. The light, we have infrared because we have the red to violet. We have infrared and ultraviolet. Now, in this region, this band, we can hear them. Many animals and creatures in nature can hear with us, as you see here. Some animals can hear frequencies much more than what we can hear, like dolphins, for example, and bats. We cannot hear the waves from the bat, okay? But it can hear that. The bats, for example, can hear ultrasonic sound. Some creatures, like whales, dogs, and can hear infrasonic, which are less than 20 hertz. For example, the earthquakes are infrasonic. We cannot hear them, but some animals can hear these waves, and they will escape. We are weird why they are escaped, like bears or any other snakes or something like that, because they hear these waves from underground. Humans also or my kind is smart. So he created many machines to here, and here. And he used that in radars and in any detectors to detect any sound, ultrasonic or infrasonic. Any question about this? Is it clear? It is simple. And just I will ask about these things. I will not go away from this. Now you see, I will solve an example. Then we will see Doppler effect, just as a video, and you know that from before. We see many times in some movies, they meet a valley and it's very down, and a hole inside the ground or in a cave, and they need to know how much the depth of that hole. They just throw a stone or a light and they start counting how long time they need to hear the sound. Then they compute the depth of that hole. Also, our parents told us, if you need to know how far is the rain from us or the lightning from us, just when you see the light, start counting seconds. When you hear the sound, you can know the distance of that lightning from you or thunderstorm. For example, if we have the light and after 1, 2, 3, 4, 5, 6, you hear the sound. The sound needs 6 seconds because the light is very fast. How far the storm from you? You just need, this is the time. You need to find x, which is the distance from the storm. It is equal to the velocity multiplied by the time. The velocity is 343 multiplied by 6. It will be equal to maybe how much? Two thousand 58 meters. It's 2 kilometers away from you. This is a simple example. But what if we have a more complicated example, which is just like that in the book? It's a good question for an exam. If we have a will, and we know the depth of that will to the water surface, and this depth is 50 meters. In this direction, you can tell me it is a negative because it is a depth, but it's okay. Let us talk about 50 meters. And you throw a stone as a free fall. You didn't throw it, you just a free fall experiment. I'm asking how much time ellipses before you hear the splash. Okay. We have 2 parts. The first part, the time required to reach the bottom, then the time required for the sound to go back to hear it. So the total time is equal to t go down, then t back up, right? Okay. How can we find the time required from the stone to reach? Simply, x equal to x naught plus b naught t plus 1 over t to g t squared. We are in y direction, so it is not x, it is y. Okay. If we assume this is the 0th level, then this is negative 50, right? Y0, it is 0. Velocity initially, it is 0. over 2. G. If downward is a negative, then G is a downward. It is negative. Negative 9.8 meters per second. Yeah. G, it's the acceleration. T squared. So we have negative sign with negative sign, we can cancel. And T, which is a square, we can find it, it is 2 multiplied by 50 over 9.8. We don't need the square, we need just T, which is the square root. It will be 3 point something, I think, 3.194 seconds. This is the time required to reach the surface of the water, the bottom. Now, what about the sound? It is 50 meters. It is not too far, not far distance, long distance, and it is not small also. It needs time. And this time is distinguishable by our ears. If we, let us compute this T2 or T going up is equal to the velocity of sound. No, it is yes, it is that y divided over the velocity of sound. Now from here to here, it's a distance. We can assume it delta y. It is at the 0th level. It is 0 minus. It is negative 15. So it will be positive at the end. Okay, over v, which is a 343. This will be equal to 0.146 seconds. Our ear can distinguish this. You can distinguish if there is a change in time by hearing. So the total time is equal that plus this 3.194 plus 0.146. It is equal to 3.34 seconds. That's it. Any question about it? It is just the velocity multiplied by the time is equal to the distance. We know that from the first lecture. This is the first law. I write it with. Now we will talk about Doppler's effect. Doppler's effect is the effect happened to the sound for the moving object with the observer. Also, I will show you this video. I need to share.
With 40 grams of protein and 1 gram of sugar. But it takes heart.
The Doppler effect was first described in 1842 by Austrian physicist Christian Doppler. Today, it is used in astronomical measurements, in Mossbauer effect studies, in radar and modern navigation, in studying the motion of stars, and to search for double stars. It is also an integral part of modern theories of the universe. But what is it exactly? Perhaps it is best explained by an example. Imagine a bug in a pool of water. Every time the bug moves its arms and legs, it makes waves in the water. If it moves its legs and arms once every second, an observer standing a few feet away would see a wave come toward them every second. If the bug remains in the same spot and does not move, observers all around the puddle would also see waves coming toward them every second. But what if the bug were to start moving toward the right while still making movements with its arms and legs at the same frequency of once every second? Then, to an observer standing to the right of the puddle, the incoming waves would appear to be at a faster frequency than the waves approaching an observer standing to the left of the puddle. This is because the observer to the right is closer to the bug, and therefore the waves, than the observer to the left. This, in essence, describes the Doppler effect. Another way to explain it is with the example of an oncoming ambulance. When an ambulance approaches you, its siren has a higher pitch as it is approaching than when it is moving away. This is also because of the Doppler effect. It might seem simple and self-evident, but it is an important concept. In 1845, Dutch chemist and meteorologist Buys Ballot tested the hypothesis using sound waves. He found that a sound's pitch was higher than the emitted frequency when the sound source approached an observer, and lower than the emitted frequency when the sound source moved further away from the observer. This happens because the sound waves compress as they approach the observer. This increases the frequency of the wave, and the pitch rises. As the waves recede, the observer will hear a lower pitched noise because the sound waves stretch out. This decreases the frequency of the wave, and the pitch falls. Meanwhile, French physicist Hippolyte Fizeau also stumbled independently on the same phenomenon in 1848. This has led to the French referring to the Doppler effect as the effet Doppler-Fizeau. Finally, also in 1848, Scottish civil engineer, naval architect, and shipbuilder John Scott Russell made an experimental study of the Doppler effect that proved Doppler's theory. Today, the Doppler effect even has applications in robotics. It is used in dynamic real-time path planning to help in the movement of robots, such as in robo-soccer. It can also be used in some types of radar to measure the velocity of detected objects, and in echocardiograms to generate an assessment of the speed and direction of blood flow. But where the theory finds perhaps its most prominent use is in astronomy. The Doppler effect is used to calculate the speed at which planets, stars, and galaxies are approaching or receding from us. It even helps us find and study new alien worlds. It seems the Doppler effect is a versatile concept indeed, with many useful applications. Can you think of another one?
Doppler effect application. Not just in sound, but in all the waves, electromagnetic waves and sound waves and seismic waves, any waves. That's all. And I'll ask you simply about this, the Doppler effect and Kepler's laws and the tides. That's all for these two chapters for today. Any question about this? Okay. Okay, I'll stop recording at this point.